Tuesday was this emission line spectrum. So this was the evidence that tells us that when we look at the electronic structure of the atom, that electrons exist in very particular holes around a nucleus, okay, or within an atom. Okay? They can't just be free-floating everywhere within the structure. They have to exist in very particular locations, sort of. Okay? And what we're looking at within the emission line spectrum is that we can see this evidence because when we look at that emission, we notice that we don't get a continuous spectrum of energy or light coming out of it. We get very particular bands, very particular energy levels, and that energy level comes back to light. Okay, so the visible light emitted only happens in a very small section for particular atoms. Okay? Bohr was the one that took this information and kind of expounded on it. And if you really want to actually see it, you'll probably want to look at the leftmost screen so you can see those blue dots. Okay, what we're looking at is different orbitals. And so what he postulated was that what ends up happening is that we've got our electrons, say for hydrogen, existing in an orbital. And when we pumped that electric current in to generate our atomic line spectrum, that electric current excited the electron. And it jumps up to a different energy level. Okay, if there weren't orbitals, then that electron can jump to any energy level. Okay, if it jumps to any energy level, when we look at the emission spectrum, we would expect to see all colors. Okay, so what he said was we don't see all colors. We only see very particular color bands come out of this. That must mean that when the electrons jump, they can only jump to steps. They can't jump up a ramp, effectively. Okay? And the light that we end up seeing after that is that when the electron then says, okay, I'm at this excited state, doesn't like being in that excited state, and relaxes back down to the ground state and releases light. Bad idea to use the formula. Let's just say releases light. Okay? That light is what we're seeing with the atomic line spectrums. Okay? So for a particular type of energy, we're going to look at a particular jump between those orbital levels. Okay, so we end up with this process, or this thing known as quantized energies of our orbitals, as opposed to a continuous spectrum. So we're looking at steps as opposed to an even ramp. An even ramp would give us an atomic line spectrum of all of our colors. We don't get lines, we just get this full spectrum of light. Because we have individual lines, we know that we have steps within it. Okay, so that's kind of the big conclusion of what we get out of our atomic line spectra. So that summarizes it again. This kind of quantifies it a little bit more. What we're looking at is an electron moving between very particular orbitals. So for the violet color that we end up seeing, that's an electron moving from energy level 5 to energy level 2. Right? You'll notice that that's a relatively large gap. Why would that be a large gap to generate purple light as compared to red light? Purple light is a higher energy light than red light. So if we look at where our red line shows up, it's the gap going from 3 to 1. Relatively a much smaller gap.
So it has more energy when it relaxes than when it's excited?
We release more energy when we relax from an energy state 5 to an energy state 2, as opposed to an energy state 3 to 1.
But does it always happen like that? Is it bigger the gap?
Yes.
When it relaxes than when it's excited?
Okay. So we're looking at the action state of it going from an excited state to a ground state. Every single time it's going to release energy. How it releases it, at this point, all you're concerned about is it releases it as light. Okay. What if we tried to do a jump, say, from, interesting question, 7 to 1? What color light would we expect?
It looks
Thank you. It has to be a higher energy than purple because we're looking at a larger distance than the 5 to 2 jump. That larger distance means more energy must be released. So what color is it? We have no idea. We can't comprehend that color because it's outside of the visible spectrum. It's outside it towards the higher energy because we're looking at a larger gap than our 5 to 2, and our 5 to 2 was purple. So if we have more energy than purple light, we're looking at an ultraviolet transition. Okay? Kind of makes sense?
Is violet light the highest energy light?
Purple is our highest energy visible light.
That's why ultraviolet means beyond.
Yep. Yeah. That's how I actually remember it. Okay? So, atomic fingerprints. So a couple people started to allude to different things like this. What we've got is our full continuous spectrum, which is what we would expect if our electrons could exist anywhere within an atom. We'd expect that full line because our electrons could jump between any different energy at any random point. We would expect all sorts of light being emitted. Okay? Or absolutely no light. Okay? Those would be our two possibilities. If we go through and look at different atoms, you'll notice that we get slightly different emission spectrums. We get different lines coming out of this. Why might we get different lines? Right, we're looking at a differing amount of electrons within our atom. We're also looking at a differing amount of protons. If we change the protons, do you think that might change the energy of the electrons?
Yes.
And potentially the energy of the orbitals that hold those electrons? Yeah. So we do end up seeing some variation within these. Okay? And yes, we got all these bright, colorful things popping out of it. If you take, oh, thanks, no neon. That was nice. If we take neon, our characteristic color for neon, that kind of, what is it, reddish? Well, I forget what it was. Okay? There ends up being 5 or 6 different lines within it. But if we add all of those colors together, we get the reddish color that we expect. Okay? What does that mean? If we get the color white, what is the color white composed of?
Is it like all color?
It's all colors. Okay? So what we're doing is adding the individual wavelengths of energy together to get the overall color that we see. When we're looking at the atomic line spectrum, what's happened is we've polarized them, okay, separated that sum energy out into individual line spectra that we can then interpret and look at. And that's what we end up seeing within these. Okay? Because every atom has slightly different energies, slightly different amount of electrons, slightly different number of protons, we expect a slightly different atomic line spectrum. We can use this as an atomic fingerprint. That's what the textbook's referring to. So if we take a look at helium versus lithium, you'll notice that those line spectrum don't match. Well, why? Is helium different from lithium? Yeah. So this is kind of fun because we can then look at any light source, because that light source is coming from some energy, okay, which is probably atomic. We can start to predict something about what atoms are present to release that energy. So we could look at the sun and say what atoms are likely present on the sun based on the light emitted from it, okay, by deconstructing the atomic or our line spectrum. Kind of neat. Okay, so what do we do with this? What we're going to start looking at is what I'm calling electron homes for the moment, but it's the same thing as an electron orbital. Okay, so we can call this an orbital as well. So we've got these different energy levels, and we want to start putting electrons into our atom. Okay, so what I've got drawn on that left, and this is very quickly going to get erased, is an increase in energy. And I've got 2 lines drawn on here. Okay, that black line and a blue line. What do you think the black line represents?
No energy.
The lowest energy possible. Where would we expect that orbital to be? Close or far from the nucleus? Really, really close to the nucleus. So when we look at this, we're saying that this is close, and this one is really far away. What happens as I move that electron further and further away from the nucleus? Eventually, what's going to happen? I think about two magnets. We take magnets, we align the opposite ends so they're attractive to each other, right? That's what we're getting here. The electrons are attracted to the nucleus, hence that's how we build the atom. But what happens as I slowly pull the magnets away? Eventually, I can let go of them, and what happens? They stay apart. So what's happened is we've pulled the magnets so far away that they can't see each other anymore. The same thing is going to happen with protons and electrons. As we start putting our electrons in, eventually we're going to get the electrons so far away that they're no longer attached. That far away is what we refer to as the vacuum. Uh-oh. UUM? Is there two C's? Dang it. Here. Nothing present. There we go. Can't spell it, think of a new word. All right. So, eventually as we add our electrons in, we're going to start putting them at higher and higher energy levels until eventually the electrons are so far away that they're no longer part of the atom. Okay. Why do we have to put them at higher and higher energy levels? Why not just put all of our electrons as close as possible to the nucleus? We do run into a space, which comes back to fitting, but why? Why is there not enough space? Electrons, remember, have 1,872 the mass of a nucleus. So if we take a nucleus, it is massive in comparison to an electron. I could probably fit a ton of electrons around the nucleus, really, really close.
Well, they're the same charge. So
There's the same charge between our electrons. So as we put electrons into the same space, what happens? The electrons get crowded with each other, not with the nucleus, but crowded with each other and say, go away. And they push the other electrons away. So what ends up happening is we're going to look at different energy levels as we go through and build our atoms. Okay, those energy levels we could characterize in this fashion. Okay, I've color-coded them only because it looks prettier. There is no red, orange, yellow, green, blue parallels with these. Okay. You'll notice that when I went through and did this, they are not evenly spaced. Okay. That is a repercussion of moving the electrons further from the nucleus. Okay, so we end up with this uneven spacing of our energy levels. So now the question becomes, how many electrons can we put into an energy level? Or let's, actually even before we do that, let's come up with some way to label these energy levels. When we talk about them, we can say, oh, this is energy level. Okay, good way to go through a number, I like that. We've got energy level 1, energy level 2, energy level 3, 4, 5, 6, 7. So we can refer to each of those energy levels. And those of you that were watching very, very carefully with what I was doing might understand where these energy levels are coming from. Energy level 1. How many electrons can we put into that energy level? But we said electrons repel, so let's just say we can fit 1 for the first sake of argument. We put 1 electron in there. How many electrons would we put into the next energy level? Same issue. Electrons repel, 1, 1, 1, 1. So the most amount of electrons that I could put into this diagram would be 7. Does that explain all of our atoms? We've got a lot more atoms than just 7. So that doesn't quite work. Okay, so one of the things that ends up happening is that each energy level can hold a varying amount of electrons depending on its energy level. And there's some characteristics that go with that. Within an individual orbital, we can only fit 2 electrons. Okay? So a different type of orbital. So let's go through and say we can fit 2 electrons into each of these. If we fit 2 electrons in, how many electrons do we get total? 14. Does that explain our periodic table? No. So there's also something else going on here. What's up?
which one is closest to the nucleus?
The closest to the nucleus is our lowest energy at the bottom.
Okay.
This one's our closest. Okay. start to see if we can come up with a pattern on what's happening with these. In your first energy level, you can fit 2 electrons. In your second energy level, you can fit in your third, it's 18. Fourth, a whole lot more. I can't do the math on that one actually. 32. Where are we getting these numbers from? I remember when I went through and counted the energy levels, there was that pause. So I was numbering up to figure out how many to number. Okay, anybody notice where I looked? Looks at the periodic table. Periodic table gives us some information. Let's start to build our atoms. We put in 1 electron for hydrogen. Where would that electron go? Our first energy level. Right? 1 electron for hydrogen. We move up to helium. How many electrons would we expect there? 2. Where does that second electron go? Right next to it, that first orbital. Now let's go to lithium. Where's that next electron go? Goes up to the next energy level. What's interesting about that? What happened? Where's lithium on our periodic table? The next row down. I said we could fit 8 electrons in here. So we had lithium. What happens with beryllium? The next electron goes in. Boron. Next electron goes in. Carbon. Next electron. All the way through to neon. Running out of hands. Or I mean fingers. One of the above. Neon. There's our 8 electrons. What happens when we move from neon to sodium? We had to add another electron, and that means we move to the third energy level, which happens to be the third row on our periodic table. The rows on our periodic table correspond to the energy levels of the electrons being put in, at least to a first approximation. And what do I mean by the first approximation? Okay. If we look at that third energy level, we'd say 18 electrons. If we look at that third row, how many columns do we have? Only 8. Why can I get 18? We're missing 10 electrons. How many columns are in between? 10. Okay. When we built the periodic table, we've got this transition metal column or sequence of elements inset one step lower. So when we look at our periodic table, our energy levels for our main groups, so the first 2 columns and the last 6 columns are our main group. Okay. The energy levels track perfectly down. 1, 2, 3, 4, 5, 6. I lost count. 1, 2, 3, 4, 5, 6, 7. 7 rows, 7 energy levels. What happens when we move to our transition metals? Scandium is at energy level 3. It's been inset 1 section down, okay, which seems a bit odd, but we'll get to that in a second too. Okay? So, kind of building these electrons in, we can start to count across our periodic table to determine how many electrons can go into an energy level, as long as we understand this inset issue when we hit our transition metals. When we hit energy level 4, it jumps up again. Why does it jump up again? Because our lanthanides and actinides are that next inset. They're further inset within this, and they're going to be 2 off because we've already shifted the transition metals by 1. The lanthanides and actinides are shifted 1 off as well. Okay, so our periodic table can tell us how many electrons are in those energy levels. It's a little bit tricky to deal with it, but we can get them in there. Okay? So the next part of this, we really only said we can fit 2 electrons into an individual space. We can't put more than 2 electrons in the same space because then those electrons repel each other. Okay? So why, when I move from energy level 1 to energy level 2, can I fit 6 more electrons? there's more space. Okay? What we're referring to as the space is the orbital type. Okay? As we move up in energy levels, we end up introducing a new type of orbital. When we start at energy level 1, there is only one possible orbital type. When we move to energy level 2, we'll have the same orbital type as we had for our first energy level, plus an extra. Because we moved up in energy, might as well add an extra orbital type. Okay? If we go through and count that out, does that give us the correct number? We said 8 electrons in our second energy level. Right? How many electrons according to this diagram? If we now have 2 orbital types, we can fit more electrons in. How many electrons would we expect to put in now? Expect to put 2 electrons here and 2 electrons there. That gets us 4. Still doesn't quite work. Okay. Turns out as we change the type, we also end up changing something else, or introducing something else. And that's something that I would like to refer to as the orbital orientation. Okay. The orbital orientation, if there's a different orientation, I can classify that as a new orbital, and it can fit more electrons. I don't remember. Oh, apparently I didn't put it on here. Within the orbital orientation, we would address that this orbital, this new orbital, which looks like a 3 now, it's not a 3, it's a bracket, has 3 possible orientations. So what does that mean for us? 2 electrons there. Come on. 2 electrons, 2 electrons, 2 electrons, which gets us our 8 total electrons for our second energy level. Okay. Yes, that does sound a bit vague and nebulous at this point because we haven't defined what we're looking at for each of these. And we'll look at that in a second. The last thing that we can really address is this electron spin, which you won't have to worry about too much. But the reason we can really fit 2 electrons into any orbital is because of electron spin. Remember, electrons repel each other. That negative to negative is bad. Okay? So within an individual orbital, okay, one orbital, I can still fit 2 electrons, and that's because the electrons spin opposite directions. Okay? It's just enough to negate that negative-negative repulsion so that I can fit 2 in. Okay? So that's pretty much all you need to know about the electron spin. You get 2 electrons per orbital. Questions about this? A little bit crazy, right?
Yes.
Okay. So let's try and bring it back to reality a little bit. What we're really asking in each of these cases is where do the electrons live? Okay. Try to explain now where you live. Okay. If you had to explain to somebody that knew nothing about where you live, what would you tell them? Okay. If you're explaining to someone from India where you live and you tell them what type of house you have, is that going to help them get there?
Geographic location.
What do you mean geographic location? I like the idea.
Like the country,
The country. Okay. What country are you in? That's our bulk energy level. Okay. Then what else could you tell them?
states.
The state that you're in. That's looking at our orbital type. What else could you tell them?
City.
City. We're now looking at an orbital orientation. Okay? So what we're looking at with each of these is a way to address where the electrons are. Okay? And we could go with state, city, street. We can even look at an actual address on the street. All of these characteristics that we're talking about, energy level, type, orientation, and spin, are just a way of defining where the electron exists. Just like when you mail something, you have to define the number on the street that you live, and the city in which you live in, and the state in which that city locates. Okay? Same thing is happening here. Okay, what makes it really tricky is it's incredibly tiny and we can't see it. But it's the same concept. Okay, does that help clarify it a little bit? Okay. I like the pause I gave you there to think about that question before moving on. What's happening with our orbital types? I remember, as I said, as we move up in energy, we can increase the number of orbital types. So at the first energy, we have only one type of orbital. Okay? And that one type has no orientation effects because there's only one orbital available at that energy. Okay? Well, what's the shape that can allow for only one possible orientation? A sphere. If I take a sphere and turn it, okay, perfectly shaped sphere, we could even think of that silicon ball thing that was 1 kilogram that we looked at that video real briefly. If we pick that up and turn and rotate it, can we tell that it was rotated? No. Same thing's happening here. So our first energy level, okay, is this sphere shape. Okay, just like we did with the energy levels, we want to come up with a name for it, so we don't just keep calling it sphere shape. Because I know I get tired of that. So what do we want to call this sphere shape? This is a good idea. Let's go with S, because sphere begins with S. So we now have an orbital type. Okay, our first orbital type is S. As we move up in energy, up to the second energy level, we're going to maintain that type of orbital. So when we go up to our second energy level, look at our first, we just have one orbital. When we go up to our second energy level, which I think I had in blue, that split into two types. Okay. The lowest energy of those two types will be our s orbital. Okay. Except now, is it the same as our first energy? Or is it a different orbital? It's different. So how could I go through and name it so that I know when I put electrons into this s orbital, I know that it's different than this s orbital? Where did this s orbital exist? What energy level? The first energy level. Where did our blue energy one come in? The second. So what we can do is go through and introduce 1s and 2s. What's that next orbital type? Okay, well, that next orbital type is this guy here, the dumbbell shape. Okay, so we've got these two lobes. If we take that shape and I turn it, can you tell that I turned it? Okay, for instance, if we do, I guess, the pseudo hang loose, my thumb and my pinky here, and I turn it, can you tell I turned my hand? Yeah. Can you tell I turned my hand? Yeah. We've got three primary directions in which we can turn the P shape, which means we end up with how many orientations? 3 possible orientations. So that orbital splits again into 3 orientations. Each of those orientations is a p orbital. A p orbital at what energy level? They're all 2p orbitals. How can I tell the difference between those p orbitals? We can look at what axis the p orbitals are on. So when we looked at our 2s versus our 1s, we didn't really care about going beyond the energy level because the names were distinguishable already. When we move up to the p orbitals, okay, I now have 3 orbitals that are all called 2p. There's no way for me to really distinguish them. So if we want to, we can tag in some extra information. That information would be px, py, and pz, which happen to be the axes of a 3-dimensional Cartesian coordinate system. Okay. Do we need to specify the x, y, and z? And when we looked at our 1s versus our 2s, why was it really, really important to distinguish those two from each other? They're in different energies. When we look at the 2p orbitals, are they at different energies? No. Is it absolutely critical that we distinguish them? No, because they're all the same energy. So typically we ignore the px, the py, and the pz. That just gets dropped off. So that's what we're building up to. The name, oh, I forgot to come up with a name. So our dumbbell, what do we want to call our dumbbell shape? That's an awful lot of words. I already gave you an answer. We call it the p-type orbital. Why p? Because there's a soft p. Look up the spelling of dumbbell. There's a soft p in front of dumbbell. Right next to the word gullible in the dictionary. P just happened to be the name we came up with. Maybe it's German. I don't know. But that's the orbital classification name that we've given to that orbital. So we've got our S and we've got our P. Yes?
Where is the nucleus in all of this?
The nucleus is in the dead center of all of these. So in the S orbital, we can't really see it because it's a sphere. Our nucleus is in the middle of a little ball. So we could pretend that we can see through it with a little X-ray vision, and they're ready to go. In the case of our p orbital, it's again in the dead center. What happens when we move up to the third energy level? We'll still have the S, but it'll be the 3s. We'll still have the p, but it'll be the 3p, because we're now in the third energy level. But because we've moved up in an energy level, what does that mean? We also have more space. We have another orbital type. That new orbital type is depicted here for us. What does that orbital type look like to you? Okay. Flower. Maybe people are too old for that. So we're looking at some kind of flower shape. The standard notation that chemists have come up or scientists have come up to refer to this as is the four-leaf clover. So it's our clover shape.
Maybe if you made that one green.
I didn't draw it. If you blur your vision, it turns green. What name do we decide to call this? Because four-leaf clover shape is a lot more effort than any of the others. D. Because in German, the word for four begins with D. Maybe it doesn't. Okay, well, I tried. Starts with D. So we've got these three types of orbitals. What happens as we move up in energy to the d orbitals? Well, now how many possible orientations do we get? And this is where it turns into a huge freaking mess. We get 5 possible orientations that come out of it. And we'll look at all of these shapes in a second, because our next slide has that. So as we move up in energy, we increase the possible orbital types. Each of those orbital types then has a type of orientation that comes off of it, which generates a new orbital that we can actually put electrons in. So if we look at our orientations with the sphere, how many ways can we orient a sphere? 1. So we get 1 orbital. The dumbbell, how many different ways can we orient the dumbbell? Actually, we get 3, and yeah, that's definitely kind of hand-wavy because I could have done this or that. But officially, we only got 3. We're simpletons. Focus on just the 3 axes. So we get 3 possible orientations, and if we want to draw them out, we could look at it where we've got 1 in what they're labeling the x-axis, 1 in the y, which is coming in and out of the plane at you, which is why it's kind of angled like that, and z, straight up and down in the plane. So we get those 3 possible orientations. We move to the d orbitals. These ones with that cloverleaf shape become even more confusing. And we look at that, we end up with, oh, don't I have a pretty picture? There it is. 5 possible ways to orient the d orbitals. And you'll notice what happens with that last one. That doesn't look like a cloverleaf shape. So where are these shapes coming from? All of these shapes come out of hardcore quantum physics and quantum chemistry, depending on your perspective of it, that takes a very long time to derive how these geometric shapes come about. What we've picked for each of these, okay, for the overall shapes, is actually, I think I had that on the last slide, now that I think about it. Put it up there, yeah. Our shapes are the 95% probability. So what someone went through and did is said, as our electrons move around within these shapes at a particular energy level, when it's at that energy level, where could it exist? And they then solved the mathematical equation, which is this big, long, nasty-looking thing. Okay? And at the end of that, they say, oh, when I solve that, that gives me the equation of roughly a sphere. I solve that, that gives me the equation of something that's roughly a dumbbell. I solve that, it gives me something that's roughly a cloverleaf. Okay? So they're all mathematical solves to determine these. And in each case, what we're looking at is the 95% probability. So if I have an electron in a 1s orbital, or let's call it a 3s because it says 3s, where can that electron exist? Can it be out here?
No.
The shape is what probability? 95%. Can my electron exist outside that shape? Absolutely it can. But 95% of the time, I'll find it inside. Okay? Why do we run with the 95%? Because if we went through and drew a picture and said that actually what we see for the s orbital is something like this, everybody would shoot me. Okay? And I want to avoid that. I think it's a bad idea. Okay? What we're looking at is just random data points of where someone could find the electron. In most cases, it's found in that general sphere shape. If we went through and did the dumbbell, we'd see the same thing. It's just someone doing a dot pattern, okay, for existing where or showing where those things exist. Okay? Kind of tricky, but what you're responsible for is recognizing the individual shapes and the number of orientations that come out of this. So when we look at the s orbital, the question I might ask is which of the following is the correct shape for an s orbital? Sphere, dumbbell, cloverleaf, donut. Answer would be sphere. For p orbital, which of the following is the correct shape? Sphere, cloverleaf, donut, none of the above. None of the above. Okay, so you're responsible for recognizing what the shape is and what the name that we associate with the shape. The next part that you're responsible for is knowing how many orientations for an individual type of orbital. If I tell you you have a p-type orbital, you tell me that there are 3 orientations. If I tell you you have a d-type orbital, you tell me there are 5 types of orientations. Okay, is that information buried in the periodic table? Yes. We'll look at it in just a little bit when I got the periodic table up here. Questions about what we've talked about so far? Okay. So, now what we want to do is be able to come up with a way to describe each of our elements and where the electrons exist within those elements. Okay, so we want to come up with what's known as our electron configurations. So we need to know something about how our orbitals fill. Where do we start putting electrons? In the first orbital, which was the 1, energy level 1, s orbital. And we can dump an electron into it. What happens if we add 2 electrons now? We move up to the configuration for helium. When we go up to helium, how many electrons does helium have? 2 electrons. So my configuration would be, where do I put the electrons for helium? 2 electrons. Where do they go? They go into the 1s orbital. Do we go up to the 2s?
No.
Nope, not yet. Because the s orbital can hold 2 electrons. How do I specify that the s orbital has 2 electrons? How about that? 2 1s electrons. Or is that the 21st energy level? Oh, that didn't quite work. Try again. 1s. Could put a 2 right after it. That could make sense. Except as I move up to the next energy level, I end up with this. So now I have a 1s and a 22s. No, that didn't work. Okay, so we could do a subscript or we could do a superscript. Which one do we choose to do? Superscript. Interesting idea. Why? What's the formula for the sulfate ion? So sulfate, what formula? SO4 minus 2. What did I write in the upper right-hand corner? The charge. The charge was ultimately our balance of electrons and protons. Okay? The charge, for the most part, is going to tell us something about the electrons in the structure. Because what happens if we change the protons? Changes the element. So the upper right-hand corner really gives us a lot of information about the electrons. So when we go to our electron configurations, where should we specify the amount of electrons? Upper right-hand corner, because consistently in all of our other systems, where do we specify our balance of electrons? In the upper right-hand corner. Kind of makes sense? Okay. We can fit 2 electrons in. Right, we're looking at that opposite spin thing that we talked about. Let's take a look at lithium's electron configuration. What happens with lithium? How many electrons do we have? 3 electrons. Where do those 3 electrons go? Where do we put the first one? The first energy level, the first orbital type. How many electrons can fit into that orbital? Where do I specify the 2? Upper right-hand corner. How many electrons have I drawn into my electron configuration so far? How many do I need to have? 3. Where does that third electron go? Our 1s orbital is now full of electrons. I can't put any more there, so I move up to the second energy level. What's the first orbital available to me in the second energy level? S. How many electrons go into that orbital? 1. Is there another way to draw this? Okay, well, we had just had up there was the electron configuration for helium. I would argue that we could also call this the electron configuration for helium and 1 electron in the 2s orbital. Did that save me much time writing it out? No. But what if I asked you for the electron configuration of calcium? Where's calcium? How many electrons does it have? It's got 20 electrons. To draw 20 electrons in, that's a lot of 1s2, 2s2, 2p6, 3s2, 3p6. Okay, that's a lot of drawing out. Could I simplify it? I could go to K, except the reason we don't use potassium's electron configuration is it's not full. So what we'll use, in this case, we used helium, not because helium was the one right before it, but because helium is one of our inert noble gases, where our electrons are fully saturated within an energy level. So for calcium, I can abbreviate calcium as, with 20 electrons, I can say it's going to have the same electron configuration as argon, with its fully saturated outer shell, plus 2 extra electrons. Those 2 extra electrons are located in what energy level? Our energy level 4, and the S type with how many electrons? 2. Now, instead of drawing out where all 20 electrons are, I've abbreviated this very, very swiftly and quickly. Okay, so it's just a way to shorthand your electron configurations. Okay. The rest of this chart goes through and summarizes how many electrons we can fit into each energy level, which we already talked about. Our second energy level fits how many electrons? 8. Because when we look at our periodic table, that second row has how many columns? 8. Okay. And we could go through and summarize all the way down and through, and we've got all of those possible electrons in it. You'll notice that the highest orbital type that we go to is F. Is it possible to get G?
Yes.
Yeah. Why have we not found G? what happens as we start adding electrons in? Keeps going in, and the electrons keep going where? Further and further from the nucleus until eventually they're no longer attached to the nucleus. So theoretically, we could come up with more orbital types. But the issue is that we've gone so far away from the nucleus actually has no attractive force on the electron anymore, and the electrons are in the free vacuum instead. Okay? So yes, it is theoretically possible. We don't have to worry about it. So we already kind of went through how we could place our electrons into our orbitals. So we go from the lowest energy first, and we start working our way up. Where we run into an issue is when we hit that third energy level. Okay, that third energy level, you'll notice we go from sodium to magnesium and then to aluminum. So we filled our 3s, sodium, magnesium. Then we jump to the 3p of aluminum, then to the 3p of argon. The next electron we would predict goes into the 3d. But the electrons for potassium and calcium go into the 4s. And the question becomes is why? Well, as we scale up higher and higher, what ends up happening to the gap between our orbitals? The gap between this orbital and this orbital is now virtually nothing. I'm not even sure I can draw a nice little arrow in there to show that gap. Okay. And what ends up happening is our atoms say, well, that balance out is so weak. I would rather have one orbital that's half filled than have 5 orbital types where nearly all of them are empty except for one. So what our orbital does is it starts to promote electrons to higher energy states, okay, which aren't that much higher, to kind of give it an overall symmetry to the structure. So there's a lot of symmetry associated with this. It goes, well, we don't believe in symmetry. Symmetry doesn't make sense. Think of the most beautiful or handsome people that you know. Okay? Evaluate their symmetry. Drop a line right in the middle of their face. And you will notice they are very symmetrical. Why? Because we are attracted to symmetry. Okay? It is something that we do naturally. Okay? Could boil all the way down to our electronic structures or our electronic nature. Okay? Our atoms follow that same idea. They want something symmetrical. Okay? So they will promote electrons into a higher energy state, which is technically more unstable, to maintain symmetry. Okay? But it can only do that when the gap between those energy levels is small. That gap gets just small enough when we hit our third energy level with our D to 4s. Okay? Yes, that's tricky. There isn't a whole lot you can do about it except just know that that happens. Okay? So we would hope that there's another way we could organize this. We can look at a filling diagram. So somebody went through and noticed that we could draw out all of our energy levels like we've been doing and kind of connect a diagonal line through them to describe the filling order. So when we put our first electrons in, where do we put them? 1s. Then we move to the 2s. Then we move to the 2p, then 3s, followed by the 3p. You'll notice on the diagonal we hit the 3p, or we hit the 4s before we hit the 3d. Right? So this diagram is supposed to help you remember the order in which we fill our electrons, that we fill the 4s before we fill the 3d. Okay? I kind of argue that's not all that important because you either memorize, you fill the 4s before you fill the 3d, or you memorize this chart. I think the chart is harder to memorize than 4s before 3d. Okay? So when we look at our electron configurations, we just want to make sure that we evaluate these things appropriately. The next issue that's going to come into play here is this concept of valence electrons. Right? When we look at the electron configurations, or we look how any two atoms interact, we bring two atoms close to each other. What's the first thing that's going to start to interact between those two atoms? The electrons, number one, and then which electrons? the ones that are furthest away from the nucleus, the ones that are on the outside of the structure. Because those electrons are going to be the first ones to interact. When we look at our chemical properties, those are the electrons dictating the chemical properties. Because they are so important in the contribution to our chemical properties, we give them a special name. Those are our valence electrons. Okay, so it's the electrons in our outer energy shell, okay, the ones furthest from the nucleus. Questions on that before we go to the periodic table to hopefully simplify this a little bit. Because remember, we're chemists, we always have the periodic table on us. Okay, so I see you on the street next week. I'm going to say, where's that periodic table? And you'll pull it out of your wallet. I used to have one, actually. I don't anymore. Hi. Any questions with these? Hi. So let's take a look at our periodic table and see if we can pick some information out of it. Okay. You will typically hear me refer to the periodic table by certain names. The most common name that I'll jump in here is that these first two columns are known as the S block. Why the S block? Because when I look at their electron configurations, the outer shell of electrons, our valence electrons for all of those elements, happen to be in S orbitals. That's why I call them the S block. If I want to look at the outer shell electrons for calcium, what's the valence shell for calcium? What are its outermost electrons? They're the S electrons for our calcium. How many electrons are there? How do you know there's 2?
20.
No. It's in the second column. If I looked at potassium, its outer valence shell is what type of orbital? S, because it's in the S block. How many electrons go into it? 1, because first column. Interesting. Okay. Let's jump to now the next section of the periodic table. The nice little green circle that nobody could see. We'll pretend that's there. Or can you see it? You can kind of see it. I refer to that section of the periodic table as the P block. Why? Because if I look at the highest energy electrons in that grouping, they will be found in the P orbitals. Where's the highest energy electron for boron? What orbital? P. How many electrons go into those P orbitals? Only 1 P. Why? It's the first of the P block. 1 electron goes in. What about neon? Where's the outermost electrons for neon? What orbital? What energy level? 2. What orbital type? P. How do you know it's P? Because it's in the P block. How many electrons should go into that P orbital? What column is it in the P block? The 6th column. How many electrons should go in? 6. Okay. We can use the periodic table to give us some information about our electron configurations. We don't have to go through and fill manually. We've got the periodic table to tell us. How about sulfur? Outermost electrons for sulfur. What energy level? 3. What orbital type? P. How many electrons? 4. Interesting. Let's bring in our full concept of valence. Our valence electrons are the electrons in the outermost energy. Are there other electrons in the 3rd energy level? Where do we start filling electrons in our third energy level? We start with which orbital? The s orbital. We're in the third energy level, so it's the 3s. How many electrons go into that 3s? 2. How do we know that? Track back through our periodic table to the s block. To get to sulfur, what do I have to do to the s block? I need to put in 2 electrons. Otherwise, I can't make it to the sulfur. Okay? What we now have is the valence electrons for our sulfur atom. So sulfur has a total of 6 valence electrons. So if we're asked the question, how many valence electrons go in, we could come up with 6. So we could backtrack it all the way through, or the next option, let's count through. We fill our S first. Our S is in which column? First and second. So there's 1, 2. We then jump to our P block. Starting with boron, we go 3, 4, 5, and 6. Our 6th column nails us with our sulfur. Guess what? How many valence electrons does sulfur have? 6. The number of our columns can help us predict that. Another thing that we could use to predict it, look at the sulfur column title. So up at the very top, there's a sequence of letters and numbers. What's that sequence say? 16. 16 minus 10 is 6. How many valence electrons does sulfur have? No way. Really? That's kind of cool. What's the Roman numeral for sulfur's column? 6. How many valence electrons does sulfur have? Really? Those numbers can't make sense. I must have just made that up. Let's try silicon. How many valence electrons does silicon have? Okay, let's do its electron configuration first. Silicon is in what energy level? 3. First orbital that we would fill would be the s orbitals with how many electrons? 2. We move to our 3p. How many electrons for silicon? To get to that element, we need 2 electrons, which means we have how many electrons? 4. What's the column title for silicon? 14. 14 minus 10? Yes. Roman numeral. 4. Huh. Valence electrons are given to us straight off the periodic table. We don't have to think about crap. This is why the periodic table is awesome. Okay? We did a really, or we, somebody else other than me, did a really good job organizing it and providing all this information up on that table. Okay? Takes a little bit of training to go through and find and get used to, but it's there. You don't have to deal with these orbitals all the way through it. Yes? There is a reason I left the D block out. Okay? The D block and the F block do not work as nicely. Okay? We would have to go through and backtrack the D block through the valence electron count that we went through and totaled. Right? So if we take a look at zinc, what's our electron configuration for zinc? It's in the 4th row, but it's part of the D block, which meant it's actually 3D. Oops. How many electrons go into those D orbitals? 10 electrons. How do we know that? If we look at the D block, where is zinc? In the 10th column of the D block, meaning how many electrons need to go into it? 10. Okay. To get to zinc, what did I have to pass through first? I had to pass through the S block. The S block is at what energy level? Our 4s2. Okay? So our filling order for how we put electrons into our orbitals is actually found on the periodic table too. We fill through our 4s before we move into the 3d. That's why the 3d is offset by 1 sequence, because what they're trying to tell you is the electron configuration. They're giving you information about how you put those electrons in. Okay? I forgot what your question was. Did I answer it?
Valence electrons would be 10 or 12.
So our valence electrons here get very, very tricky. Okay? This is also the issue with this. Valence electrons are typically applied from organic chemistry. In organic chemistry, our periodic table is drastically simplified to look at primarily, oh, this one doesn't have it on it, carbon, because carbon is our organic molecule. What orbitals are involved for carbon? S and P. So when we look at our valence electrons, we're typically only concerned about the electrons located in the S and P orbitals. We don't look at the D electrons, at least for this class or for the rest of your Gen Chem careers. Okay. If you're interested in it, yes, there's a massive amount of chemistry involved in the D orbitals. It's known strictly as inorganic chemistry, and I know they call general chemistry inorganic. It's not. Okay. It is sort of, but it's more general than anything else. So if you were actually concerned in how different metals interact with other species, how we can make solar cells, or how we could do other various things, different materials, a lot of that settles into the D block. Okay? So periodic table gives us lots of information about how we fill, okay, and where we put those electrons. That can help us build our electron configurations with knowing very little else. Okay? A lot of information I know. Takes a little bit of practice. Once you pick up the practice, you'll be fine. Are there exceptions to these? Yeah. Thankfully, the exceptions don't show up in this class, so I don't really care. If you need help with those exceptions in future classes, feel free to come back and talk to me, and I'll help you try and nail those down. Last parts of Chapter 5, we look at this concept of ionization energy. All right, so this is now bringing in some more definitions. Ionization energy is the amount of energy required to remove an electron from an atom in its gaseous state. Okay, so the most important part of that is how much energy does it take to take the electron out. Okay, this is important because it says ionization, so we just think, oh, how much energy does it take to make an ion? That's not strictly true. Okay, it's how much energy does it take to remove an electron. If we remove the electron, what charge does the atom become? Going to have to become positively charged. So let's take a look at carbon as an example. Carbon has how many protons? 6 protons. How many electrons? 6 electrons. What happens if I remove an electron? Becomes 5. If we go through and do our math on this, we've got 6 times the charge of a proton, which is positive 1, plus 5 times the charge on an electron, which is negative 1, and we get an overall charge of positive 1. So when we're looking at the ionization energy, we are making a cation in this process. If we go through and now tie in our understanding of electron configurations, we can start to understand the patterns that come out of our ionization energy. In general, as we increase the energy, okay, if we go from, as we go from the bottom to the top of our periodic table, the ionization energy increases. Does that one make sense? So we're taking which electron, by the way? The outermost, because that's going to be the easiest to pull off. We might as well be comparative or do a fair comparison. If I take the outermost electron from francium versus the outermost electron from hydrogen, which one is presumably easier to get? Why francium? The electron is held much further away from the nucleus. So it's going to be a lot easier to pull it off because francium isn't really guarding it. If we take a look at hydrogen, hydrogen's a vicious little jerk down there with its really close to its electron, and it's going to fight you to take it away. Okay? The next trend is not so easy to look at. Okay? As we go left to right across the period of elements, okay, in general we see it increase as we go left to right. Why might it increase? what happens as we go from left to right on our periodic table? We increase the number of protons and we increase the number of electrons. When we went up a column, we're locating the electron in a different energy state. When we go left to right, does our energy state change? No. So we're putting more electrons in the same space. Okay? So the distance is no longer a factor. What is a factor is that our nucleus has also gained more protons. So as we go from left to right in the table, our electrons aren't further away. They're actually held a little bit tighter to the nucleus because they're now closer to a more positive nucleus. Okay? Those are our general trends. Okay? Do we see exceptions with these? Yeah, we see those exceptions because our electrons are actually going into orbitals, which are at different energy states. The s orbital is officially lower than the p orbital. Right? It's those variations within it that cause our ionization energy to change. Right? And that really requires looking at the electron configurations. So let's take a look between, let's say, lithium and cesium. Right? Where are they located relative to each other? Same column or same group. Right? Our trend said what? Going to be higher ionization energy to remove the electron from lithium. Right? Because the electron is much closer to the lithium atom than it is to the cesium atom. If we look at our trend, what was the trend between lithium and cesium? Right? Do we actually verify that trend? Yeah, lithium has a higher ionization energy than cesium. Okay? Not by much, but that's not particularly relevant. Okay? We're just looking at it in general trending that way. Let's take a look at lithium versus magnesium. What happens? We're going left to right on our periodic table, which means in general we would expect ionization energy to increase. If we take a look at it, what happened? Lithium goes up to the next point. Our next point is the next element, which is, I said magnesium. I should have said beryllium. Sorry. Beryllium. What happens to the ionization energy? It increased. And that's because what happened is we increased the number of protons. The more protons, the tighter they'll hold the electrons. Okay? Because our electrons are being put into the same energy level. Here's our first exception. What happens as we move from beryllium to boron? Our trend should say boron should be a higher ionization energy. Turns out it's lower. Why? Look at the electron configuration for boron. It ends up being, boron. We've got 2s2, 2p1. What electron are we trying to remove? Which electron is our highest energy electron for boron?
The one on the p orbital.
The one in the p orbital. So if I remove that, what happens to the symmetry of boron? Goes down to 2s with 2 electrons in it. That looks really symmetrical. Nicely paired, everything looks pretty. Yay, we're happy. Okay? So boron's like, hell yeah, I'll get rid of that electron. Sounds pretty awesome. Okay? Now I look pretty. Take a look at beryllium. What happens to beryllium? It started symmetrical. When I ionize it, it becomes less symmetrical. Okay? So boron's going from an unsymmetrical state to a symmetrical state. So it says, yes, I want to do that as quickly and easily as possible, which means a lower ionization energy. Beryllium, on the other hand, starts symmetrical and goes slightly unsymmetrical, which means it says, no, I don't want to do that. It's going to require a higher energy. We can apply that same rule to each of these little bumps. Okay, you'll notice the bumps that I'm pointing at are only when we're looking at our s and p transitions. You'll notice I won't make any comments about what's happening within the d orbitals. Okay, why not? because the d orbitals are punks. They get all sorts of weird stuff going on within that. You get all sorts of weird things happening. You don't want to look at the trends within the d orbitals. What we're concerned about is the trends within the main group systems. What will you be tested on? The overall trends, not the exceptions. So as we move down a periodic table, what happens to the ionization energy? What was that? N or D? Decreases, right? Because we're getting the electrons in further orbitals away. As we move left to right, what happens to our orbitals? They stay in the exact same position, but the positive charge increases, which means our electrons are now held tighter. Our ionization energy should increase as we move left to right. Okay? The next thing I kind of want to talk about here, it's not in your textbook, so I'm going to kind of gloss over it, is this concept known as electron affinity. Okay? It is the opposite of the ionization energy. It's the energy released to grab an electron from the vacuum. So our electron floating off in the vacuum, very high energy state, there's nothing balancing it out. So if our atom reaches out and grabs that electron and absorbs it, now the electron is partially neutralized by our nucleus. We have less charge, everything is better. So we're looking at now an energy release to pull that electron in. Each of our atoms is going to have a slightly different affinity for that electron, or its ability to grab that electron. Right? That affinity can be correlated just like the ionization energy. Right? And we can see trends within that same idea. What charge does the atom become? It's going to become negative because now we've increased the amount of electrons. Okay, so the reason I'm addressing this is that we had in one case a positive charge, in the other case a negative charge. And if we looked at our charges on our periodic table I told you to memorize, you'll notice that our nonmetals were all negative and our metals were all positive. And the reason for it is the balance between the electron affinity and the ionization energy. That balance is what's known as, just lost connectivity. Oh, maybe it's there. Electronegativity. Electronegativity is a wickedly important concept that is severely lacking within your textbook, particularly for those of you that have to move into organic chemistry. So if you're going from 130 to 230, electronegativity you need to understand. Okay? Electronegativity is the ability for an atom to take a bonding or take electrons from a bond. Okay? We haven't talked about the bond yet, but we'll get to it. Okay? The balance of our electronegativity is deciding, does our atom have a high electronegativity, in which does it want electrons? If it wants electrons, what charge does it become? Negative. Or a low electronegativity, it says, get the electrons away from me, I don't want them. Which means its charge becomes positive. What charge were our metals? Positive. What charge were our nonmetals? Negative. In general, what would we expect for our electronegativities? Our metals should be low, and our nonmetals should be high. Where's the most electronegative element on the periodic table? Fluorine, located in the upper right-hand corner, our classic nonmetal category. Where's the lowest electronegativity element? Cesium in our lower left-hand corner. Classically, the most metallic element. Being able to tweak and understand electronegativity is going to allow us to manipulate and determine what types of bonds we see, Chapter 12, which we'll talk about next week, and how we can predict different interactions, okay, and charges. I definitely have to stop there, even though we got to the fun part. I think we only have a couple more slides, yeah. We'll look at ionic charges, and then we're done with Chapter 4 and 5. We'll be moving into 6.